Now here, we're going to go through the basics of an Ellingham diagram. This line tells us standard Gibbs free energy. So that's delta G naught. How can we make use of this information? So the engineer who is trying to, say, perhaps extract copper from copper oxide can figure out exactly what is the PO2 or equilibrium pressure for oxygen very easily from the Ellingham diagram. Let's just assume that the furnace operates at this temperature. All he has to do is draw a line downwards, and the point where delta G naught and this line intersects will give you information for PO2. In this case, PO2 must not exceed 10 to the power of -9 or else it will oxidize. So the engineer in the control room, without having to make very complex calculations, will be able to control the PO2 or the pressure of the oxygen to keep it below 10 to the power -9 in order to get pristine copper. We talked about this reaction earlier, and this reaction corresponds to the pink line, the first stage oxidation of copper. This pink line represents the equilibrium whereby CuO is stable and below the equilibrium line, Cu2O is stable. Now, what about this reaction? This reaction can be represented by this blue line, where below this Gibbs free energy, at these temperatures, copper will be stable. So, in this very simple Ellingham diagram, people who work in factories, such as metallurgists, will be able to take reference very quickly without doing massive amounts of calculation, the necessary temperatures in order to, say, keep copper stable, especially if they are trying to extract copper. How can the engineer make use of an Ellingham diagram? So we have already determined that this line is essentially delta G naught, which is the equilibrium Gibbs free energy. Let's say the furnace operates at this temperature over here. If the engineer in the control room wishes to get pristine copper, he has to figure out what exactly is the equilibrium pressure for O2 and make sure that the pressure is below that. So he can just draw a line downwards. Once he figures out the operating temperature of his furnace, and this point where they intersect will be able to give you the PO2, which in this case is 10 to the power of -9 atmospheres. As long as the engineer keeps the oxygen pressure below 10 to the power of -9, he will get pure copper as a product. If it exceeds 10 to the power -9, the copper will begin to oxidize. So you can see exactly how important Ellingham diagrams are in order to maintain stable furnace operations. We can finally move on to trying to understand the full Ellingham diagram. There are three important things you need to know about this. First of all, the Ellingham diagram plots delta G naught against T, temperature. Also, know that oxides of lines at the lowest are more stable than the higher lines. So let's, for instance, take two examples first. Titanium and silicon. Say you are operating a furnace where you wanted to extract pure silica and all you had was silicon dioxide. Because titanium is more stable than silicon, you could throw some titanium into the mix and it will be able to capture all the oxygen to form titanium dioxide, and its product will be pure silicon. One of the most classic examples of how it's used, or how this principle is used, is the example of a melt containing aluminum, which is somewhere over here. Silicon, carbon, which is this flat line over here, and iron, which is this line over here. Assuming you have a furnace that operates at 1500 degrees Celsius. If you were trying to perhaps extract pure silicon, you could throw in some aluminum and it will, because it's more stable, extract all the oxygen and reduce silicon dioxide to silica. So that is one way we can use these principles, and the engineer operating the furnace does not have to do complicated calculations in order to figure out what pressures to inject oxygen into the entire melt. The last thing to note is that the stability of oxides is dependent on its temperature. For instance, here, at room temperature, iron is more stable than carbon and it will rust. However, at 1500 degrees Celsius, the opposite is true, and you can actually use carbon to get pure iron. So, how can an engineer make use of the Ellingham diagram on the fly? Let's just say, hypothetically, an engineer is trying to perhaps extract silica from silicon dioxide. The first thing to do is to identify the location of this oxidation line. Let's assume that the engineer is currently running his furnace at 1000 degrees centigrade. First thing to do is to draw a line from this corner to intersect the oxidation line and extend the line all the way to the end of the diagram. From there on out, he will be able to read out the PO2. Perhaps here it's 10 to the power of negative 38. So the engineer who is operating the plant knows that he has to keep the partial pressure of O2 below 10 to the power of negative 38 in order for him to be able to extract pure silica. Above this pressure, the silicon will oxidize spontaneously. Now, what happens if we say we ran the furnace at a slightly higher temperature, 1500 degrees centigrade? First thing you do, once again, draw a line from 1500 degrees centigrade to intersect the oxidation line and construct another line through all the way until you get a readout of the pressure, which is somewhat about 10 to the power of negative 18. And you would know that to get pure silicon, you would have to run the partial pressure of oxygen at less than 10 to the power of negative 18 in order to get pure silicon. So you can see how engineers who are operating furnaces will be able to get these values very quickly purely by a series of intersecting lines. So another way of controlling the O2 pressure is perhaps by introducing H2 or hydrogen. So let's assume that we've got a melt, we've got H2 going in, and here we've got multiple oxygen molecules. By introducing H2 to oxygen, we will form H2O or water, which will instantly vaporize, thereby reducing the oxygen pressure within the melt. So let's just say, for instance, we would like to reduce titanium dioxide to pure titanium. The first thing we do is to identify the oxidation line. Next, since we are pumping in hydrogen, we can identify the intersection point through the operating temperature of the furnace, in this case 1500 degrees Celsius, and then draw a line straight through to find the pH2O to pH2 ratio, and that is this second scale over here. So likewise, other than just pressure, we can control the O2 pressure by controlling the ratio of H2 to H2O, and we can also determine that from the Ellingham diagram. Now the final method of being able to control the O2 pressure is by using carbon monoxide. By introducing carbon monoxide into the melt, it will react with the oxygen, forming carbon dioxide, which just goes into the atmosphere and reduces the oxygen pressure. How do we use this information? For instance, say we wanted to reduce silicon or silicon dioxide to silicon. We identify where the oxidation line is, and then we draw a line starting from the carbon marker all the way through its operating temperature of 1500 degrees centigrade. And from here, we can read the ratio through this very first scale to give us the PCO2 to PCO ratio. So at the beginning of this course, we went through the fundamentals of thermodynamics, exactly how we can apply them to things such as ideal gases. In the second half of this course, we finally made use of the principles that we learned, applied them to solid solutions, and we rounded off with nice examples of how we can use them in real life. Thank you very much for joining me in this course, and I hope you have learned something along the way.